All right. So, in the last video lecture, we have discussed about principles of minimum potential energy. Okay. So, in that, we have highlighted that the main feature of that approach is that, in addition to check if the configuration is in equilibrium, it will be possible using principle of minimum potential energy if the equilibrium configuration is stable or unstable. Okay, so in this lecture we will briefly discuss a couple of example problems in which we apply the principle of minimum potential energy to solve the mechanics problems. Okay, so we are going to discuss some examples on principle of minimum potential energy. Okay, so we're going to solve some problems using principle of minimum potential energy. Okay, so let us consider a problem 1 in which we have a rod AB. Okay, so we have rod AB. So AB is weightless rod, okay, whose weight can be neglected. At B, there is a torsional spring attached to it. So at B, there is a torsional spring of stiffness KT. T denotes torsion. It's 500 Newton meter per radian. Okay, so the stiffness of the torsional spring is the amount of moment that is required to produce one a unit angular displacement. Okay, so at A, weight W is attached. Okay, so what we need to find is the maximum weight W for which stable configuration can exist in this vertical position. This is what we need to find. Okay, the moment you see word like stable equilibrium or unstable equilibrium, you know that we have to use principle of minimum potential energy. Okay, the moment you see stable equilibrium, we need to use principle of minimum potential energy. Okay, so let us assume a deformed configuration of this problem. So let us give a small displacement W, small displacement theta. Okay, and then the stable configuration, and then the deformed configuration is shown in red. Okay, so if this is L, okay, this is L cos theta, and this is our origin. Okay, the origin about which we measure theta. Okay, now let's write the potential energy of the system. So potential energy of this system V, there is a gravitational potential energy that is coming from the weight plus elastic potential energy from the spring. So this is from the spring and this is due to the weight W. And it is mentioned that the weight of rod AB is neglected. Okay, so now V is W L cos theta right, and So the gravitational potential energy is WL cos theta plus the elastic potential energy stored in the spring is half kT theta square. Okay, for equilibrium, dV by d theta is 0. Okay, which implies that kt theta minus WL sin theta is 0. Okay, and in the problem it is given that L is 2 meter. So we are interested in the equilibrium configuration in the vertical position. Okay, so in vertical position, okay, theta is 0 and this satisfies dV by d theta is 0 condition. Okay, you substitute theta is equal to 0 in equation 1, you see that the equation gets satisfied. So the vertical position is a possible equilibrium position. Okay, so for stable equilibrium, d square v by d theta square is greater than 0, which implies kt, right, minus WL cos theta should be greater than 0. So W should be less than kt by L cos theta for stable equilibrium. Okay, so the limiting value is, so the limiting weight for stable equilibrium is W is 250 Newton. That is the answer for this problem. Okay, so when W is equal to kt by L cos theta, that is when we get a limiting value for stable equilibrium. Okay, so I hope this will be clear. Let us move on to the next problem. Okay, so we have rod. So rod AB is hinged to the center of the circle, so that is the origin. Okay, that is our origin, and on the rod weight W is attached. Okay, so let's say this is A and this is B, and this is connected to a spring with stiffness K. So the length of rod AB L is 2 meter. Okay, and this R radius is 1 meter. Okay, so the radius of the pulley R is 1 meter. Okay, and the spring stiffness K is 8 Newton per meter. okay, and weight W is 50 Newton. Okay, so what we need to find is that the problem statement is when rod AB is in vertical position, the spring is unstretched. Okay, now we need to determine all possible angles of equilibrium by possible angle we mean this theta. Okay, determine all possible angles of equilibrium and comment on their stability. So this is what we need to do. We need to find angles theta for which this system is in equilibrium and comment about their stability. As you know, the moment we are going to that our interest is in on stability of the equilibrium, we have to use principle of minimum potential energy. Okay, now let's write the potential energy of this configuration given the angular displacement theta. Okay, so potential energy V is half K. The displacement of the spring is r theta square plus WL cos theta. Okay, elastic potential energy stored in the spring, gravitational potential energy due to the weight. Okay, as you know that for equilibrium, okay, so dV by d theta should be 0. That will be by substituting the value of K, L and W, you get 8 theta minus 100 sin theta. Okay, it should be 0. So we need to find theta, all possible theta for equilibrium. So you know, if you solve, solving 1, okay, we get theta is 0 degree. This you can write it from direct observation of this equation itself. So one possible equilibrium configuration is theta of 0 degree, okay, which means the rod AB is in vertical position. Another solution is 166.55 degree. Okay, this you have to find by applying trial and error procedure. Okay, this is not a simple algebraic equation, so we need to employ trial and error procedure to find this solution. Okay, so we have two possible equilibrium configurations. Okay, two possible equilibrium theta. Now to find the stability of equilibrium positions, okay, to find stability, we compute the second derivative of potential energy, which will be 8 minus 100 cosine theta. Okay, when theta is 0, which implies d square V by d theta square will be minus 92, so which is less than 0. So this is an unstable equilibrium. Okay, so when theta is 166.55, d square, okay, sorry, v by theta square is 105.25, which is greater than 0. So this is stable equilibrium. Okay, so we started off, so to solve any mechanics problem using the principle of minimum potential energy, we need to introduce a small deformation in the system. Okay, and then we write potential energy for the deformed configuration. Then you apply equilibrium condition, which is first derivative of potential energy, and then to find stability of the system, we investigate the second derivative of the potential energy. Okay, so this is the standard procedure to solve any mechanics problem using using this principle of our interest. Okay, so for this particular problem, we have found two possible equilibrium configuration. One of them is a stable equilibrium, another one is an unstable equilibrium position. Okay, all right, so we have solved two problems. We will discuss one more and stop this lecture. Okay, the third one involves the problem we are going to discuss involves slightly a complicated problem. Okay, so okay, so let's say a problem. Okay, so what we have is a rectangular block. Okay, let's say this height is h and this is n r. Okay, we are going to discuss what r is. Okay, and this is a rectangular block and a semicircular block. Okay, a semicircle of radius r. Okay, they are made of same homogeneous material, so both are made of same material. Okay, and they are secured together and placed on a flat surface. So what we need to find is find minimum radius r in terms of h, or in terms of h for stable equilibrium considering two cases. Okay, considering the width of the block, considering width of the block nr is equal to the diameter of the body. So nr is 2r equal to the diameter of the body, and width nr is equal to h. Okay, so we need to find r as a function of h for these two special cases. Okay, so this is what we need to find. Okay, so now this is an undeformed configuration. Okay, and you can see that this is symmetric with respect to this axis. Okay, and the centroid C is located somewhere there, and we denote that as h. Okay, so C is the centroid of this configuration. Okay, so this is an undeformed configuration. Let us draw the deformed one. So this is a slightly a tricky one to draw. So let's see. Okay, so this is deformed like that. Okay, and that is the axis of symmetry. Okay, and your centroid is here. Okay, so if we mark, so this position is radius r. Okay, and this distance is h minus r cosine theta. Okay, and this is the value of theta. Okay, so now the potential energy for this configuration, so potential energy V is mass of the entire system, mg, r plus h minus r cosine theta. Okay, because the centroid is located at a distance of r plus h minus r cosine theta from the reference point here, from the ground. Okay, so we know that for equilibrium, is it clear? How do we write the potential energy of the system? So the centroid is located at a distance of r plus h minus r cosine theta from the ground. The potential energy is mgh. Okay, this we know. Okay, so for equilibrium, dv by d theta should be 0, that is mg r minus h sine theta. Okay, so the only possible equilibrium configuration is the only possible physically relevant equilibrium configuration is theta to be 0. Okay, all right. So to investigate its stability, we need to see d square v by theta square for theta is equal to 0. Okay, which is mg r minus h cosine 0, which is greater than 0. Okay, so we have written the potential energy of the deformed configuration. For equilibrium, you know that the first derivative should be 0, and the possible equilibrium configuration gives you theta should be 0. For stability, the second derivative should be greater than 0. Okay, so the only possibility is that So this implies R should be greater than H for stable equilibrium. Okay, so the radius R should be larger than the, or H, the centroid should be located within the semicircle for this to be stable. Okay, all right, so that is the limiting case. So the limiting case for stable equilibrium is R equal to H. That is the limiting case. Okay, which means that the centroid of the composite body should be here. So if we have this configuration, okay, so it is here. Okay, so the centroid should be here. Okay, that is the limiting case. That is the condition. Okay, so if we define the axis to be here, so what it means is that, let us say the centroid of which color to use, let's say the centroid of rectangular block is located here. Let's say this is y2 bar, and let us say the centroid of the the semicircle is here, located at y1 bar. Okay, so the equilibrium or the centroid of the composite body will be at the red circle if a1 y1 bar is equal to a2 y2 bar. Okay, for this equilibrium configuration. So a1, by 1 we mean semicircle, by 2 we mean rectangle. So area of the semicircle is pi r square by 2, and y1 bar is 4r by 3 pi, we know that. Okay, so a2 is nothing but nr times h, and the centroid is h by 2. Okay, so from here you get h is 2r square root of 3n. Right, and then there are two cases specified. So case 1 is nr is 2r, which implies n equal to 2. So minimum radius for stable equilibrium r is going to be 3 n h by 2. So n is equal to 2, you substitute here, you get r minimum is going to be 1.22 times h. Okay, then the second case is that, sorry about this, so case case 2 is that nr is equal to h. Let us denote this by another constant a. So r minimum, you substitute this in the equation 2, you get square root 3n by 2 n times r min. Okay, h is n times r min. so it implies n is 1.1, so our minimum is 0.9086 h. All right, so this problem is slightly involved. If you are not able to understand it in the first in the first go, you see this video once again of this part. If you have any question, you send me an email or post it in the Google Classroom. Okay, thank you very much.